Ngalakin Khadijan Nyunga Boja.
And line voltage, and also the relationship of the phase voltages and the line voltages for a balanced Y pattern voltage source. Okay, so this thing has been done in last week. Should be okay. Let me check where is the okay. This part is done. Okay, quickly let's have a look what happened here. So this part is done, right? Let's move on to the next part. So it's a quick summary regarding the Y connection. So we call the voltage across each element of a Y-connected device as the phase voltage and then phase current, line voltage, line current. Okay, all these stuff are very fundamental concepts for the Y-connected pattern. And at the bottom of the slide, we can see some important relationships between the line-to-line voltage to the phase voltage and also the line current to the phase current. They are very important, not only for this chapter, but also for many, many chapters until the chapter 6, okay? So please make sure you understand this one. After we review the delta connected pattern, we may reverse back to this page to compare difference, okay? So this is a Y connection pattern. So for this Y pattern here, these features are important. First of all, if the connection is in Y connection pattern, the line-to-line voltage is longer and leading. The longer means the magnitude is stronger. The leading means the phase angle is leading the phase angle of the phase voltage. But how big are they and what's the leading angle? Okay, from this equation you can see here, this V line means the line-to-line voltage. That means the voltage across two transmission lines during the transmission. And this V phi is the phase voltage. With that, line-to-line voltage is stronger than the phase voltage. How strong is it? Square root 3 times stronger. If we say the phase to phase, the phase voltage is 1 volt, so the corresponding line voltage will be square root 3. That's the magnitude. Okay, so stronger. And leading, so the line voltage phase angle should be 30 degrees greater than the corresponding phase voltage. This 30 degrees means leading angle. Or in other words, if you think this is our phase voltage, V phi, for a single phase in the three-phase power system, the line voltage will be leading. Leading means 30 degrees greater. Why we draw this direction pointing up? Because in the complete plan, the counterclockwise is the positive rotation direction. However, when I write on my tablet, did you see the blink of this screen? Okay, my screen is blinking anyway. So the counterclockwise direction is positive. So this leading means for this line voltage, its angle is 30 degrees greater than the angle of the phase voltage. And longer means the magnitude. So this is the magnitude of the line voltage. So we say 2 bars around the VL indicates the magnitude of it. The magnitude of the line voltage is square root 3 times bigger than the magnitude of the phase voltage. Okay, so this plot is corresponding to our first equation here. Okay, and so everyone, so when you make notes on this thing here, please remind yourself this is true only for under 2 conditions. First of all, must be balanced the system, and secondly, this connection pattern must be the Y pattern. Okay, so this is the for the voltage. The other thing, the second formula regarding currents. So in the three-phase power transmission system, we have the line current. The line current means the current transmitting through the transmission cables, right? And we have the phase current. The phase current is current flowing through a single phase at the load side or at the voltage source side. Okay. So what is the relationship between the line current and the line and the phase current? If you go back to our connection here, so here you can see we have the phase current. Where's the line current? Line current is in the transmission line here. This is the line current. But if you focus on the connection between the phase and the line, so these two line segments are connected to one single point. If you are applying a KCL, the Kirchhoff's current law, the summation in equal to summation out. Okay? So if you are using KCL here, you can find the input current to this node must be equal to the output current from this node. So that means the phase current and the line current must be the same. Okay? So this should be pretty simple. Okay? So now we go back here. So I think this formula is simple. The very last one should be a general formula for calculating the complete power. So we are using the S to denote the complete power. Typically, not for the three-phase power system. Typically, for AC circuit, the complete power S, so I use this draft note, okay? S equal to AC voltage. This AC voltage is not only the magnitude. It contains both of the magnitude and the angle. In other words, this V may be like 10 volts with 30 degrees stuff. It's a vector. It's not a number, okay? The S, the complete power, equal to V by I conjugate. This star indicates the conjugate operator for the complete numbers, okay? So this is the general formula calculating the complete power for AC circuit. But in the three-phase power system, one single three-phase power system is a combination of three individual AC circuits, and they are all balanced. So when you calculate what is the total complete power for a balanced three-phase system, you just need to evaluate the complete power for each individual AC circuit and multiple 3 to get total power. This number 3 is indicating you have 3 individual AC circuits in this three-phase power system. And the V by I conjugate is indicating using the phase voltage multiple the conjugate of the phase current to get the complete power for one single AC circuit out of 3. So is that clear, everyone? Yeah. I think Tyrone has done this part, so I just quickly review that part. This is for the Y connection pattern. Now we are moving to the next topic. So actually, we have 2 options for the patterns used in the three-phase power system. The Y pattern has been discussed. The next one, the one showing on the screen now, is the new one. We call that as a delta. So normally, if you call that as triangle pattern, I don't mind. It's the same thing, okay? So delta pattern is shaped just like triangle. And so I'm not going to just go through all the formulas again, so you can read through this mathematics in here. Actually, all the formulas given in this slide are just try to use the KCL to analyze the relationship between the line current and the phase current. Why do you say this is using the KCL? Say here, let's just make one example using the first one. IA equal to IAB minus ICA. The IA on the left-hand side means the line current. IAB is the phase current in the AB phase. The ICA is the current in the CA phase. In other words, on the right-hand side, the IAB and the ICA are the phase currents. All these 3 terms are combined at one single point in the circuit. And out of these 3 currents, the line current IA is out from the node. ICA is out. ICA is out. IAB is in. Sounds good? By using the KCL, for a given node, the summation of the input current must equal to summation of the outgoing current. So for this question here, we got 1 in and 2 out, right? So the input current will be IAB. The outgoing current will be the line current IA and the ICA. Then if you move the ICA to the left-hand side, then you derive this relationship. For the other 2 equations, roughly the same idea. So this is not so news to you because in our foundation units a long time ago, you have already learned this stuff. So this is just a review. Okay? And now we are coming to the feature diagram for the so-called delta pattern. If you have looked at the diagram given on the left-hand side of the slide, first of all, you can find the easiest thing, voltage, the line-to-line voltage. So where is the line-to-line voltage? For example, let's focus on the phase A, phase B, or line A and line B. The AB line give us VAB. This VAB is the line-to-line voltage, the voltage difference across line A and line B. And now let's just focus on the phases. So regarding the phase AB, which one is the phase voltage? Phase voltage is voltage. It's voltage across a single phase. This is also called VAB. This VAB is saying within that particular phase, what's the voltage difference? But this VAB is actually the voltage difference across, we call that maybe node A and node B. In the meantime, the line-to-line voltage VAB is also connecting to these two nodes. So in other words, if you got a triangle or the delta pattern, the line-to-line voltage must equal to the phase voltage. This is true no matter if the system is balanced or not. Okay, this is depends on the feature of the connection only. Okay, so these two. Regarding current, so now we have understood regarding this delta pattern. So what is the relationship between line-to-line voltage and the phase voltage? Now, next thing we are going to discuss is about the line current and the phase current. So actually, in the previous slide, we have already examined the relationship between the line current and phase current. And if the system is balanced, so what's the balance again? Balance means all three voltage sources are supplying the same magnitude of voltage, but phase angle always have 120 degrees difference between each other. This is a balanced voltage source, okay? So if the system is balanced, so you can see the line current IA is actually equal to, okay, square root of 3. Square root of 3 is the scale of the magnitude, multiple the magnitude of the phase current, and then multiple such kind of a unit vector. But for this vector, the angle is negative 30 degrees. So this is indicating for a balanced delta connected voltage source or the load. So the current, the line current, will be longer. So square root of 3 times longer, but lagging. How much is lagging? 30 degrees. So if you draw this thing out, we call this as the I5. This is the phase current for a balanced delta connection pattern. So it's too long actually. Okay, this is I5 here. So where is the corresponding line current? Okay, line current will be longer and 30 degrees lagging. So will be given here. This angle between these two things is 30 degrees. But we have said in this complete plan, the positive rotation direction is going counterclockwise. So this is positive rotation direction. But this 30 degrees is going backward. So this is actually negative 30 degrees. This negative 30 degrees is corresponding to this angle difference. And the size of the line current is square root of 3 times stronger than the size of the phase current. Okay, so this is about the features for the Y pattern and the delta pattern connections. And in this page, we summarize all the details in one single table. I think the easy one is the current one. Okay, so if you got a Y connection pattern, so the line current and phase current should be same. If you got a delta pattern, so the line current will be square to 3 times stronger than the magnitude of the phase current. So this is for current. For voltage, so we focus on this entry and this entry. The first entry is talking about the magnitude relationship between the line current, line voltage, and the phase voltage. The third entry of the table is talking about the angle between the stuffs. Okay, I don't want to repeat this thing again because in the summary we have already gone through this part. Is that okay, everyone? Yeah. You got a question? Oh, good. Yeah, fine. And at bottom of this slide, you can see the circuit diagrams for these two connections. So now, next one, per phase analysis. Okay, per phase means one single phase. Why do we need this thing? So here, this analysis methodology is based on a fact that we are going to focus on balance the system only. If the system is unbalanced, so we are not able to use this methodology. But in this unit, and also in many real-world practical cases, so the systems are always balanced. For balanced system, you do not have to really calculate the power, the voltage, the current for three phases one by one, because actually the three circuits are identical. The only differences are their angles. So what we need to do is just to focus on one single phase, one single AC circuit out of the whole three-phase circuits. After you got everything you want regarding one single AC circuit, then using the relationships between the line-to-line voltage, phase voltage, phase current, line current, you can work out the corresponding values of other phases directly. So this can reduce our workload in the calculation. Okay, let's just go through this one. Per phase analysis allows analysis of balanced three-phase system. So always remind yourself, okay, that must be balanced with the same efforts as for a single-phase system. The balanced three-phase system, is all loads and sources are Y-connected. A moment ago in the review, we mentioned that there are two different connection patterns. One is a Y connection, the other one is a delta connection. But we have a way, which will be introduced later in this lecture, to convert the delta connection pattern to Y pattern. So here we can assume for all the balanced three-phase power system, the connection pattern are Y pattern. It's much easier for us to do analysis and calculation. Okay. And there's no mutual inductance between phases. In other words, you can do the calculation towards one particular AC circuit, in other words, one single phase, without considering the interaction with other phases. Okay, and then all neutrals are at the same potentials. So that means because you got a balanced system on the source and on the load, so the connection between the two neutron points is not necessary, because all the currents will merge together and cancel each other. And then, because of the neutrons have the same potential, the connection between the two neutron points is not necessary. Okay, and all phases are completely decoupled, so just individual phases in this stuff. And all system values are the same sequence as sources. Sequence, this concept, I'm not sure if you know this or not. Actually, when we started the foundation unit, we briefly introduced this concept. For three-phase power system, there are two types of phase sequence. One is called positive sequence. The other one is called negative sequence. In most of cases, for positive sequence, we call it as ABC sequence. And for the negative sequence, we call that as ACB sequence. So what does ABC and ACB mean? So that is indicating it this way. You have three phases in the three-phase power system. We call that as phase A, phase B, and phase C. If you know, for the phase A, we say we have the VA as the phase A voltage. If the phase B voltage is lagging the phase A voltage by 120 degrees, of course, we are talking about a balanced system, okay, here. So magnitudes between these two voltages are supposed to be the same. The angle, 120 degrees. And for the phase C, its voltage is another 120 degrees. But this time, lagging than the VB. Now, you got three phases, and you got three-phase voltages. And the relationship between these three voltages are given here. Sorry, forgot to mention, this is 120. And this is 120 as well. Okay, of course, like this one. So in this case here, because we define this as a positive rotation direction, and these three AC voltages are actually rotating in this plane along this direction. So the order that the voltage vectors passing through a reference point is A and B and C. So we call this as ABC sequence. So in the meantime, we call this as a positive sequence. Okay. Another case is that may happen in the real world. Okay, the vectors remain the same, but VA is reference one. The next one, which got 120 degrees lagging than A, is C, and the next one is B. Now, these three AC vectors are also rotating in the plane here. But the order that these three vectors passing through a reference point is A first, followed by C, and then followed by B. So the order is A, C, B. This is called ACB sequence or negative sequence. This may happen in the real world as well. Okay, so we have two different sequences. Okay, this is how we define this case here. So up to now, we assume for all the systems we discussed up to maybe chapter 4, we assume they are all positive sequence or ABC sequence. Before moving on to the next slide, everyone, I want to remind you one thing. Sorry, we made a small typo at the bottom of the slide. See here, A is a reference phase, right? Phase B lags phase A by 120 degrees, no problem. But see next one, phase C lags phase A. No, don't do that. The phase C is lagging the phase B by 120 degrees. Sorry about that. Okay, please just correct that. Okay, now let's move on to the next one. So don't forget, we are currently discussing this per phase analysis. Okay, so we are focusing on one single phase or one single AC circuit out of three in this three-phase power system. Now let's just isolate this one single circuit from the whole system. And in this system, we have one voltage source on the left and one load on the right, which is denoted by the Z. But on the top, you can see we have the RT, we have JXT. What are they? T for transmission. So actually the RT and the XT are the resistance and the reactance of the transmission cable. On the left, as I mentioned, you can see the VA, right? VA is the phase voltage of the generator in the phase A. And the Z equal to Z with theta angle. That is the load of the phase A on the load side. Okay, these are all the conditions. And in this question, for this single phase circuit, the active and the reactive power consumed in the load. So in other words, for these two equations, we are focusing on the load only. So how much real power is consumed by the load and how much reactive power is consumed? Okay, by using a formula. Remember we mentioned a moment ago is that the not real power, I say complete power, S, is equal to V by I conjugate, right? This is what we mentioned. But how to derive the real power and the reactive power from this complete power? You must remember that you mentioned in last week, which is called power triangle. In this power triangle, we have all the key factors included. This S is given here. S is vector having the magnitude and the angle. Okay, this is S. The horizontal edge of triangle is actually the projection of this complete power on the real power, on the real axis. This is actually the real axis. This segment is actually our real power in the unit of watts. So in addition of the real axis, of course, we have the imaginary axis. So imaginary axis is going this way, imaginary axis. So the projection of the S on the imaginary axis is actually the reactive power. So in other words, the edge of this triangle is called, normally we use Q, okay? Q for reactive power. The unit used for the reactive power is, do you know the unit? Yes, VAR. By the way, what is the unit for the S, for the complete power? VA, good. It seems I don't have to go through this thing again, right? You know this. And this angle is also important. We call that as the theta. The theta is the angle for this power triangle. This theta is related to the power factor. Power factor is really important for your study in this unit. You are going to use it many times, okay, until the end of the whole semester. So the relationship from theta to the power factor is equal to cosine theta, like this, okay? Before we move on to the next part, guys, could you please tell me how to determine the value of the theta? Or what kind of things are related to theta? That's right. Same thing, right? Yes, good. So actually, we mentioned for the AC voltage, it has the magnitude of it with the angle. I can't remember what notation used last week by Tyrone, but I gave that as CTV temporary, okay? Temporary CTV. CTV is the angle for this AC voltage. If you say for the AC current is magnitude of current with the theta I. This angle theta here, I'm using another color of pen, is actually theta V minus theta I. Okay, why minus? That is because you have such conjugate operation here. Okay, okay, that's too far away. And for this question here, after you understood this power triangle, we want you to evaluate what is the real power and the reactive power of the load. So what I'm asking you to do is, what is the P, what is the Q? But for this triangle, we have already known it, and we are able to determine the S. If the S is known, the theta is known, of course, the real power and the reactive power can be determined. So let's go back here. See here, the first formula. So 1 phi means one single phase, okay? P is the real power. The real power of this single phase is equal to the magnitude of the AC voltage multiple the magnitude of the AC phase current by cosine theta. Why cosine theta? Because we are actually calculating the horizontal projection of the S. Okay? Correspondingly, the next one, for the reactive power, same thing, but we are changing that to the sine theta. Sine means we want to find the vertical component of the complete power. So I think this is pretty simple for everyone. Is that okay, everyone? Any questions? Good. Next part, much easier. So how to determine the active and the reactive power in the three-phase load? In our initial discussion, in this part, we focus on one single phase. But now, don't forget, the system you are working with is a three-phase power. So you have to work out what is this power terms for the whole three-phase power system. But they are identical except the angles, because you got to balance the system. So what we need to do is just to multiply 3 and 3 for each individual phase power to get the total power for the three phases. Do you agree, everyone? Good? But how did we derive the next term given here? So actually, I want you to compare between the second segment and the third part of this equation. In the second part here, in the middle of the two equations, we got 3 multiple V phi I phi. The V phi I phi are the phase voltage and phase current. They are all related to a single phase circuit. But in the final part of these two circuits, we got square root 3 multiple VL IL. This VL IL are actually the line voltage and the line current. But why we have to change 3 to square root 3 when we use the line current? The thing is pretty simple, so I keep writing here anyway. So first of all, from the middle part of the equations, we can divide this number 3 to square root 3 by square root 3. That's 3. Multiple V phi I phi. So everyone sorry for that. Actually, my screen is blinking. I write on the board, on the tablet. So sometimes I don't know what I'm writing. So if you think I just give you a message writing or something wrong, just let me know, okay? So this is here. And now let's assume we have the Y connected, balanced connection. If you got a Y connected balanced system, so what does square root 3 by V phi mean? Okay, we go back in the table. For Y connect pattern, square root 3 by V phi is the V line, the line-to-line voltage. Okay, so actually this is converted to square root 3 line-to-line voltage magnitude. And also for the Y connection pattern, the phase current and the line current are equal because one in, one out, right? By using KCL. So the phase current can be replaced by the line current directly. And then, of course, multiply the same thing, cosine theta, and finish. But this is how we derive the very last part of equation from the middle part. Should be very easy, okay? Okay, after we discuss the first part, we have already known how to calculate the different power terms for the load. But in the whole three-phase power system, in addition to the load, the transmission cable are also consuming the power. So we need to evaluate how much power is used by the cable during the transmission. So in this page, so you can see the formulas. So of course, you can see for these notations, we are using the capital T as a subscript, T for transmission cables, okay, transmission lines. This number 3 in the subscript means we are considering the total real power or reactive power consumed by the cables for all 3 phases, so not a single one, okay? And the first equation is used to evaluate what is real power. The second one is for reactive power. And on the right-hand side of the 2 equations, the number 3 means, okay, you have to consider 3 cables, one for each of the 3 phases, okay? And I phi square, I phi is a phase current. But actually, shouldn't we use line current? Because actually, if you are talking about the power used by the transmission lines, so we should use the current in the transmission lines for calculation. But the current in the transmission lines should be line current. Why should we use phase current here? That's it, yes, because you got Y connection pattern. Line current and phase current are equal. So you can, numerically, you can use the phase current here. Why can't you use the line current? Because actually, the measurement of the current is very easy at the load end. But if I want you to measure what is current of the transmission line, you have to climb up 20 meters to measure the current from the cables, which is not convenient. So in most of cases, for Y connection patterns, we are using the phase current in the calculation. Okay, the calculation should be easy. Power equal to current squared by resistance, that I squared by R. So this RT denotes the resistance of a single transmission cable. Get that? So for the reactive power in the next line, same thing. But in this case, for calculating how much reactive power consumed by the cable, you must consider reactance of the cable. So you can see here, we are using the XT to denote it. Okay, so this is reactance of the transmission cable. So if you consider the whole cable, so the ZT is equal to RT plus JXT. It's just one resistance, one reactance. Okay, just that, so easy. Before moving on, guys, I want to remind you one thing. Maybe you have known that, okay? In AC circuit, when we got a load or transmission cable, whatever, normally they consider resistance and reactance. But do you know which power term are associated with these 2 things? For example, if I give you resistance RT, my question is, can the resistor here consume real power? Yes. Can this resistor consume reactive power Q? No. Resistor can consume real power only. Or you call that active power, same thing, okay? Resistor can consume active power only. Reactance cannot touch the real power. The reactance X can consume reactive power only. So in other words, if you got reactance like this, so in the S, so complete power equals P plus JQ. P is real power, Q is reactive power. This P is prepared for resistance. This Q is prepared for reactance. Good? So I think this should be pretty fundamental, okay? Okay, now after these 2 formulas, we know how to calculate the power, different powers, of course, for the transmission cable. Let's just go back to the initial see. Do we have an initial system? Quickly, sorry, 1 minute. Do we have a complete system? Okay, in this system, balanced Y connection, right? So on the left-hand side, you can see the generators. On the right-hand side, you see all the balanced loads. In between, we have the transmission cables. So the generators on the left-hand side are providing the electrical power to the right-hand side. And once the power is generated, they are transmitted through the cable and arrive at the load. Both the load and the transmission cable will use some of the power. So one supplier, two consumers. Okay? So let's go back to that formula we discussed. Where are we? Here. So in this slide, the very bottom two formulas are actually calculating how much real power and reactive power we need to provide from the voltage source on the generator to supply the power to both of the load and transmission cable. The P3G and Q3G are the total real power and total reactive power produced by the generators in the three-phase power system. On the right-hand side, the P35 plus P3T means the real power consumed by the load plus the real power consumed by the transmission cable. For the Q reactive power, the same thing. Oh, good. So actually, this is calculating the balanced system. So what is the supply, what is consumed in the system. Okay, that should be a simple question. Okay, now example. This question is a little bit long, so after this question, let's take a short break. And I hope this question should be easy and can help you to really fully understand the relationships in the three-phase power system factors. In this question, 208 volts. By the way, everyone, so when I go through the questions, sometimes I will give you some hint. In our future questions, this thing may help you to understand the question. For example, you got a 208 volt. What voltage is it? Phase voltage, line voltage, source side, load side. What does it mean? Okay, when I go through the examples in the lecture, I will just give you the information. I hope you can make some notes because your future questions, you will face the similar questions. Okay, this 208 volts voltage is the line-to-line voltage at the load side. Normally, when we talk about the voltage for a three-phase power system, we always think about the viewpoint of the users. So if you say 208, of course, we want the user to get 208 volts. If I'm thinking, okay, I'm the provider of the electricity, I give you 208 volts. But after transmission, this voltage can decay. So at the receiver side, at the user side, the voltage may drop to 100 volts. That makes sense. So all this voltage I gave here are the user side voltage. And also for user side, you may have different options. Okay, I have the Y connection pattern as users. I have the delta connection pattern as users. I don't care. I'm talking about between the transmission lines, what's the voltage at user side. So in other words, this 208 volts is the user side line-to-line voltage. Okay. Okay. For this system, it's shown in next page. It consists of an ideal 208 volts Y-connected, Y-pattern, three-phase generator. And another is what? Y-connected load through a three-phase transmission. Okay, this is just important keywords for this question. The transmission line has an impedance of 0.06 resistance plus J multiple 0.12 reactance per phase. This is about the transmission line. For the load, the impedance is 12 resistance plus J by 9. The 9 is reactance per phase for the load. Okay, so this is all conditions we have. The question is asking, A, what is the magnitude of the line current? What is the magnitude of the line current? Very easy question. Line current based Ohm's law equals, line current for the Y connect pattern equal to phase current, right? This is the first thing. And for determining the phase current, phase current equal to the phase voltage divided by the phase impedance. Okay, so let's have a look at the question first. This is diagram. So on the left, you can see the Y pattern generators. On the right-hand side, we got the Y pattern balanced loads. And in between, there are 3 transmission lines. For such 3-phase power system, this is a very typical connection. But sometimes, you may see another connection in between these 2 neutral points. Actually, this yellow connection between these 2 neutral points is totally optional, because all the power systems we discussed in this unit are assumed to be balanced. If they are all balanced, so you may think, if you have the IB here, IA here, and IC here, IA, IB, IC must balance as well. They have the equal magnitudes and the 120 degrees phase angle difference between each other. When you add up the IA plus IB plus the IC, that summation of the IA, IB, IC should give you the current flowing back through this neutron connection. But this must be equal to 0. Why equal to 0? Okay, IA, IB, IC are 3 phase current vectors. If you draw that out, IA is here. IB, IC are balanced with it. So IB, IC are given here. So same size, but 120 degrees angle difference. When you add up these 3 vectors, for example, let's just add up IB, IC first. IB vector plus IC vector should give you the IBC vector. This IBC vector has the same size as IA, but pointing to the reverse direction. So this IBC and IA will be cancelled with each other when you add them up. So in other words, for a balanced system, IA plus IB plus IC must equal to 0. That means this I current in the neutron connection is equal to 0 amps. That means no current in the neutral connection. If there's no current in this line, why do we need this line? So in most of cases, we just cancel it to save the cost for these cables. Okay, so this thing here. So for balanced 3-phase system, having or not having the neutron connection doesn't matter. Same thing. Okay. Okay, now let's just focus on how to solve the line current. Line current equal to phase current for this Y pattern, so that's easy. So now we need to solve what is phase current. Because we are using the per phase analysis, so within this single phase, the current is equal to the total voltage supply divided by the total impedance. There are 2 parts of the impedance. One is the impedance of the transmission cable. The other one is the impedance of the load. So you can see we are using an ohms law here. The current is equal to this voltage is voltage supplied by a single phase of generator. And at the bottom, we are adding up the total impedance of the cable and the load together. The ratio of them gives us the phase current, which is equal to the line current for this Y pattern. So everyone, do you think it's okay? Is that too slow or too fast? Okay, just okay? Fine, good. Yeah. Okay, this part's done. So part A is so simple, so easy, okay? And now let's just have a look at the part B. So I will not go back. Let me just check what is the part B of the question is asking. Okay, wait 1 second. Where are we? Okay, part B is asking, what is the magnitude of the loads, line, and phase voltage? So in other words, for the part B of the question, we want to determine the phase voltage and the line voltage. But on the load side, if you go to this circuit, actually there are 2 different line-to-line voltages. The first line-to-line voltage is on the generator side. For example, this 208 here is the line-to-line voltage. This on the load side, This is also the line-to-line voltage. This is load side one. This is the generator side. Okay, so these are two different, line-to-line voltages. But for this question, we want to determine what is the voltage across the lines for what? For user side, for load side. So in this case, the load side phase voltage is equal to, again, Ohm's law. You know the phase current. You know the impedance of a single phase. So just multiply these two things together, you will get the phase voltage. That's pretty simple, right? Just Ohm's law, nothing else. And then this phase voltage is actually a vector having its magnitude and angle. Magnitude is 119.1 and angle is negative 0.2 degrees. And what is the magnitude of the line voltage? Okay, again, use that knowledge we learned from the review. So for a Y-connected balanced system, its line-to-line voltage magnitude is longer. How long is it? Square root 3 times stronger than the magnitude of the corresponding phase voltage. In this part, you have already got the magnitude of the phase voltage. And this system, luckily, is a balanced Y connection system. So the magnitude of the line voltage should be square root 3 times stronger than that. So here, we are using square root 3, multiple that to get the answer. Okay, so easy stuff. And part C, we go back. Part C is asking the real power P, reactive power Q, and apparent power. Actually, when we talk about that power triangle before, I didn't say this term. That's a really easy one. So the apparent power, in many cases, is denoted by two bars around S. The S is the complete power. The two bars means the magnitude of it. So in other words, apparent power is actually the size of the S, this segment. Get that? Okay? So let's go back to the example. We want to determine real power, reactive power, apparent power consumed by the load. Okay, just use formula. Very simple. First of all, real power. Real power for single phase should be the phase voltage magnitude by the phase current magnitude by cosine theta. And if you consider all three phases together, so multiple 3 at the beginning. So now you can see in the first line of the formula, because 3 V phi I phi cosine theta. So this question here. And in the next line, it's just calculation. 3 is number 3 phases, right? By 3. 119.1, that's the magnitude of the phase voltage. That's okay as well. Phase current, 7.94. We have calculated this value before. My question is, where did you get this number? Why did you say that theta equal to 36.9? Why? We didn't calculate this angle in the first two parts of this question. And we just use it. Do you understand why? Do you remember what's theta? Okay, I draw a small triangle. This is power triangle, right? And the P is getting here, real power, Q, and S, and apparent power here. Remember I mentioned that this theta is very important for you. One thing, the theta is linked to the power factor. Secondly, this theta is linked to the AC current and the AC voltage. Theta, as Ben mentioned, is theta V minus theta I. This theta is the angle difference between the AC voltage and the AC current. But why do you say this number is equal to 36.9? Go back. For this single phase, I said this phase voltage is a vector. It has a magnitude and angle. What is angle? Negative 0.2 degrees. This is the angle for the AC voltage. In other words, here, this is theta V is negative 0.2 degrees. What's theta I? Okay, keep going back. Line current is equal to phase current, right? For this Y connected pattern. And we calculate the angle for this AC current vector is negative 37.1. That is our theta I here. So we minus negative 37.1 degrees. The difference is how much? 36.9 degrees. This angle is the angle used in the complete power and also other power calculations. Okay? Okay, this is the whole thing here. And the calculation should be easy. I leave that to you. Okay? And for the reactive power, same thing. So using the angle, but don't forget, we are using to find out the vertical edge of the power triangle. So that should be sine theta. And okay, Q, I mean, reactive power is okay. Finally, everyone, I know the notation used in the slides are a little bit confused. So for the apparent power, I always use the S with 2 bars. But in the textbook of this unit and also in the lecture slides, we are using such font for the apparent power. So sorry guys, I go back a little bit. So can you see that? If we want to say one thing is a vector having the magnitude and the angle in this unit, we always use the bold-face font, dark color. But if we are saying the magnitude of this vector, we always use the normal face font. Okay, regarding this case here, what we are doing, we are actually calculating the apparent power, or in other words, the magnitude of the complete power. I'm not using the bold face font. I'm using normal font. Okay, so this is actually calculating the apparent power. That's equal to 3 by V5 I5. So this formula was introduced in last week in the revision. So you should be able to know this one. And the calculation is given here. Got that? So far so good, everyone? Yeah. So for online students, are you okay? So if you have any questions, so online students, if you have any questions, please type your message and I will reply you shortly. Okay. Okay, keep going. Example, part D, power factor of the load. I think that's really too easy. I have told you this formula by using that power triangle. If you know theta, power factor is cosine theta. Just that. Okay. Simple calculation. I leave that to you. Next one, for the E, for the part E of the example, the real power, reactive power, apparent power again consumed by the transmission lines. So first of all, out of these 3 formulas, you can see we got number 3, number 3, number 3, because we are using 3 lines for the transmission between the generator to the users, right? So these 3 means for 3 lines. And for the formulas, I don't want to repeat that again, really simple. This I5 square is actually the current flowing in the phase, but again, for the Y pattern, phase current and line current are same. So actually, you can treat them to be the line current. Line current magnitude square multiple the resistance of the transmission cable is calculating the real power consumed by the cable. So result is given here. Oh, good. Next one, Q. Q is the reactive power consumed by the transmission line. Same thing. 3 for 3 lines. I5 is actually the IL, is the line current. Square it multiplied by the reactance X of the transmission line equals 22.7, whatever. Can you find a problem in this line? In the calculation of the reactive power? Should we use watts for the power of reactive power? Definitely not. This is wrong. Guys, sorry for typo. Correct it again. So what I should write here? Thank you very much. Okay. Finally, the apparent power of the transmission lines. So you just use the magnitude of the impedance of the transmission cable to do calculation. That. So if you do not want to do this way, if you do not like this formula, okay, you can use power triangle. Now I'm talking about the power triangle for the transmission cables. This is the Q line, the total reactive power consumed by 3 transmission cables. This is the total real power consumed by 3 cables. So P line. The question is asking you what is the apparent power. Actually, the question is asking you what is the size of this edge of triangle. That is S-line. And actually, in this triangle, one angle is 90 degrees. So this S-line is equal to square root P line square plus Q line square, which can give you the same answer. Okay. Keep going. So 2 small questions left. Okay. So part F is asking you again real power, reactive power, apparent power supplied by the generator. Remember what we mentioned in that slide here. If you want to evaluate how much power you need to provide it by the generator, you just need to sum up the power consumed by the load and the power consumed by the transmission cable. In our part B and part E of the example, we have already evaluated the power for the load, the power for the cable. So in the question F, what we are going to do is just to add up the power for each of these 2 things to be the total power supplied by the generators. Really too simple, so I skip this part, okay? Finally, power factor at the generator. This is the very last question. So what is power factor at the generator side? So here, for solving this question, we go back to our power triangle. But this time, this power triangle is for the generator. In the previous part, we have solved the real power provided by the generator is 2281, so 2281 watts. And the total reactive power provided by the generator, the vertical edge, is 1725 VAR. And this question is asking you what is power factor. Power factor at the generator side is equal to the cosine theta. The theta is the angle for this generator part, power triangle. So what's theta? Theta is equal to arc tangent rise over run. So that's I just use the symbolic notation. Okay, is the Q generated divided by the P generated. The same thing. I suppose right. Yeah. Right. This gives you theta, and then cosine this angle. You got a power factor. This is the very last part of this question. So everyone, now let's take a 10-minute break. So please come back at 10 past 4. We are going to start the next part of this chapter 1. Okay, online students, we are going to take a short break, so 10 minutes. And the next part of the lecture will start at 10 past 4. Yes, they have maybe up to 10 students. Yeah, that's it.你给我说你办公室电话吧。行，我给你拨过去。我现在正 break 呢，10分钟。那什么，那变动你觉得大吗？需要大改吗？哪个？啊。行。那可以没问题，只要 后你这边说可以搞了，那我这边随时可以弄。你是想这周办还是下周办？今天礼拜三，礼拜五可以，或者是像下礼拜一可能也行。我看看 table，我都可以。啊，然后我个人感觉要早点好，我们早点好，学院是早，那我争取吧，我看看 table 应该是 OK 的。你先别看通知，你稍等一下，那个我可以看一下他们主题什么，然后我再准备大概其实那个一个简要的一段话两段话，然后给你们一块看，让我发挥这个，你觉得行不行？行，没问题。然后具体那些我从网上做的，什么送link我都给从网上整好，这个行。稍等会儿，你稍等会儿，让我下去之后看全体结果，确定了以后你再说，给他们过一下，因为我现在上课没法查，你知道吧？行，然后那个具体那个 test paper 你自己再看一下，然后你要觉得要改的话，你改；你要就想跟我商量改，你也行，行，好嘞，那就这么着，那回来啊，再说。 Then this is good one. What do you want? No, no, pause. Last week. Either which one? I have 2 weeks. One for the you said you have 2 weeks, 2 months lecture per week. Why do you give me only 2 months lecture for the week? Why? It's unfair. So you can keep that the email. I'm not going to reply back to them. I think they will keep. I prepare 2 full 2 hours lectures for you guys. You enjoy this. Actually, this is so-called 2 hours lecture. It's limited to about 1 hour and 1.5 hours before. Which I have to handwrite something slowly. No? Wait. Yeah, no, I'm taking us just as I'm saying. I think I can high table stuff. I can recommend it. No, I'm agreeing with you. I'm saying like this is crazy. Why? Yes. It's because you need to be paying attention. So I'm there for 2 hours. I know the participation, sorry, and activity goes. So I don't know how to finish. Yeah, no, I'm glad you brought it out because I learned better about it. Oh, I have a question on that. Don't you watch the movies anymore? Really, yeah, let's give you full information. Because I just reported all the methods based on the not getting the video. But all the mathematical formulas, the concepts are very abstract and dry in this video. If you can manage that with rather the text. What I do,
I love hearing your voice.
what I do is just to read that out for you. So, but are you guys happy so far regarding my 4404 and kind of this one? Oh, good. How can you?
She was having a nap there.
Yeah.
Okay. So actually, for the 10th class, because one class twice the outcome, you have to watch the video. So if you can't manage to watch all the videos, so in the 10th class, I will go into the details that we have done in the week 1. So give you some background information before seeing that, and if I teach you, you should be able to solve the questions given in the 10 classes. So that means not 100% necessary for you to watch all the videos before attending the 10 classes. But if you can, then you can bonus. But make sure before the last test, you must have done videos, lectures, slides, teleclass methods, and everything. Our first class will come soon. You guys should be getting lucky. What happened? It's not even so many in the teaching of the foundation English, right? Yeah. This guy has to take the first class message. You look straight.
Yeah, but I was being undergrad again.
I see. Okay. Okay, online students, we are going to start the next part of the lecture, and hope you are ready. Okay. Okay, everyone. So let's keep going to the next part of the lecture. So in the first part, we have done the discussion of the example, and let's move on. So at the beginning, in the revision of the three-phase power system I mentioned, we assume all the systems we see in this unit are connected in the Y pattern. The reason is, if you got the delta balanced pattern, it can be converted to the equivalent Y pattern. So that means in the future, if you see in the test or the assignment or somewhere, you got a delta connect pattern, you must be able to know how to convert it to the equivalent Y pattern. So in this slide and next one, we are going to check this out. So how to do the conversion and why we have these results. Okay, and our discussion will be divided into two parts. The first part is how to convert a delta triangle, okay, delta connected voltage sources to the equivalent Y connect pattern. And the other part is how to connect the load to the Y pattern. I think the easiest one is the next slide, so I'd like to start from here. So how to convert a delta connected generators to the Y pattern? Actually, this thing is not new at all. You can see we mentioned if you got a balanced delta connected voltage sources, because of the line-to-line voltage is equal to the phase voltage. See here, if you are talking about this delta pattern, the delta pattern here, the phase voltage and line voltage should be the same. And if we want to convert this delta pattern to such Y pattern, in the Y pattern, line-to-line voltage should not be changed. In other words, I'm the user of your power system. I want you to give me 220 volts. I don't mind what is your connection pattern at the generator. I just want the 220 volts. These 220 volts must be given to me through the transmission lines. So transmission line voltage remains same no matter what is the pattern of the generator connections. Is that clear? Okay, so in other words, we should keep the line-to-line voltage unchanged. Regarding the Y pattern, the phase voltage and the line voltage, I think this relationship is given here. So line-to-line voltage is equal to divided by square root 3, and then with 30 degrees. So we will got the line. Sorry, I repeat again. Sorry for that. So regarding this part, first of all, between the Y pattern and the delta pattern, the line-to-line voltage should remain the same to guarantee the equivalency between these two patterns. And for the delta connection, so on the left-hand side circuit, the phase voltage must be equal to the line voltage, right? And for the Y pattern on the right, the line voltage will be equal to, I got to write this one. So square root 3 and square with angle 30 degrees and V5. This is a Y pattern, right? And for this one, this thing here. But we have said, no matter what is pattern of the generator, the line-to-line voltage must be equal. So in other words, this thing is equal to DC. Now, if we rewrite this equation, so we can say, so the phase voltage in the delta pattern must equal to square root of 3 with 30 degrees of the phase voltage in the Y pattern. Now we can derive this relationship. So for each phase in the Y pattern, its voltage equal to the corresponding phase voltage in the delta pattern divided by square root of 3 with 30 degrees. That means we are going to move this term to the bottom of the left-hand side to derive that equation. Okay? Yeah. Okay, that's and nothing new. So regarding the voltage sources, the transmission between delta to Y or Y to delta is just one single formula. Okay, very simple thing. Now let's go back to the load case. So if I want to convert a triangle load or the delta load to the corresponding Y load equivalently, this relationship must be kept. So if in the delta load you got Z phi to be the impedance, when you convert this to the Y pattern, so the impedance of the load must be changed. How to change it? Divided by 3. Why we have this result? Okay, I don't know the reason, but the proof is going to in the next 2 slides later. Okay, this one here. And let me see if I need to go through this one. But anyway, let's quickly go through this one. Now we divide that in 2 parts. On the left-hand side, so if you got a delta connected pattern, so the IA, the line current, will be equal to the difference between the 2 phase currents. And the phase current is calculated by using the phase voltage divided by the phase impedance. So we do this way by using KCL. And then the result is going to be here. Because we focus on the impedance, so the impedance of a single phase in the delta load is equal to VAB minus VCA divided by the line current. This is the result we derived from the delta part. And then let's have a look at the equivalent Y pattern. If you got a Y pattern here, in a single phase, its phase voltage is VAB. Now we are in the Y pattern, okay? That's equal to ZY. That is the impedance of single phase multiple IA minus IB. Do you understand the reason of that? This is the phase A, phase B, and phase C. So we have the connections. And in this case here, I want to evaluate what's the VAB. VAB is the voltage difference across A and B. So here, VAB is the voltage across these 2 points because VAB. Okay, VAB. How to evaluate VAB? Let's focus on the phase A impedance and phase B impedance. So in other words, I want to focus on this part of circuit connection only. In this circuit, in this line here, we have only 2 impedances, so ZA, ZB stuff. But because we got balanced Y connected circuit, ZA, ZB are equal. They are all equal to Z, or we'll call as ZY, whatever, is ZY, the same value. So if I want to evaluate what is the voltage change between A and B, so the VAB is equal to VA minus VB. VA is the voltage drop of the first phase, the phase A voltage. That's equal to ZY by IA. Minus, for the phase B, the voltage drop of the impedance at B is ZY by IB as well. And you can just extract the ZY out of these 2 terms to derive, ZY by IA minus the IB. Okay, this whole thing here. So repeating this procedure for the CA phase, you reach the similar answer. And then we found to find what's the VAB minus VCA, the voltage difference across these 2 line voltages. And then we reach this answer, so just mathematical induction. And because you got balanced system, So the summation of the IA, IB, IC should be 0. We have mentioned that, right? So this IA is equal to negative IB and minus IC. This thing can be substituted back to this equation to derive this. It's really long one. And sorry to say, I didn't ask you to memorize this thing, so it's not so important actually. Yeah.
We don't need to be able to derive that yet.
Hmm?
In a test, or is it, we don't need to
I will not ask you to derive this whole thing. I just gave you the reasoning in the class, but you are not requested to memorize this thing. It's really too simple. It's just some mathematical steps, right? And by the end, we can reach really simple, not that simple. Okay, we reach this thing here. Actually, from this step, what we have derived is this step. So 3zy equal to this thing, but this term is the same as this term. And then these two things are linked together. You got the 3zy equals to zeta, and zy equal to 1/3 of the z delta. Get that? Again, I will not request you to memorize this thing, useless. But you must know how to use it. If you see some balanced load, you must know how to convert that to the equivalent Y-connect pattern. Get that? Easy stuff, okay? If you have any questions regarding these mathematical steps, you can ask me to give you some more explanations. But I believe no one will ask me. Okay, let's move on to the next part. I think we don't have too much left in the chapter 1. And okay, next one. This is important. Okay, everyone, this is important, very important for your later chapters and also for your classes 1, for your assembly 1, assembly 2, and class test. You need to see this one and you need to understand this. Single line diagram. Actually, after we went through all this knowledge up to now, you can see I don't like to draw the generators, the load, the transmission lines, because it involves too much components and it takes so much time to draw them. You have to draw the 3 lines with the circles, with the voltage side inside. It is time consuming. But actually, we have another easier way to represent the 3-phase power system. This way is called single line diagram. So drawing the single line diagram is much, much easier. So it's customary to sketch a 3-phase balanced power system in a simple form with a single line representing all 3 phases of the real power system. Okay, one-line diagrams provide a compact way to represent the interconnections of a power system. You will see example very soon. Okay, and the one-line diagrams typically include all of the major components of a power system, such as generator, transformer, transmission lines, and loads, all that stuff. Okay, and for instance, in the following diagram, you can see the power system in Figure A can be equivalently represented by a one-line diagram in Figure B. This is the typical 3-phase power system diagram. As mentioned, very complicated. But before see the one-line diagram, we'd better to understand this complicated one first. In this system, there are 3 parties. The leftmost is the 3-phase power generators. That's easy stuff, Y pattern, okay? And in the middle, you can see a triangle with the Z5A1, Z5A1, Z5A1. That is a delta connected balanced load. We call that as load 1. On the rightmost, another load, which is connected in the Y pattern. So in other words, in this case, one power generator is giving the electricity to 2 loads, 1 suppliers, 2 users. And the transmission cables are connected between these 3 parties like this. For example, we start from this point. This is the departure point of the generator. So electricity is given from here through the transmission line. And after reaching this point, so this is given to this phase of the first load. And then keep going, given to this phase of the second load. This is the first line. And let's talk about this point. This is giving electricity and go to this point and go to this point. And finally, the very last phase of the generator is giving the electricity to here and to here. This is how the electricity is transmitted to the 2 loads and how this power is distributed in this system. we want to use an easy way to draw the equivalent diagrams. The result is given here. Much easier. So in the future, we are going to draw the three-phase power systems like this. And on the left-hand side, you can see a big circle with G1 inside. The G denotes the generator. So actually, this one single G1 circle denotes all three voltage sources in the generator part. Okay? And we mentioned this generator is giving the electricity to the other two loads. Okay, see here. I'm giving the electricity to a bus. This bus is a position which connects all the relevant parties together. Okay? So on this bus, on the right-hand side, the two loads are all connected to the generator through the bus. Just that, nothing else. And some technical details regarding the generator and the loads must be labeled around it. For example, for the generator, below it, you can see the connection pattern for the generator is Y pattern. For the two loads, the load 1 is delta pattern. For the load 2 is a Y pattern. Just that. It's just about some details which we cannot observe from this one-way diagram. So please just label them around these parties. Just that. And is that easy? Oh, good. So guys, I will reverse back to the first page quickly, okay? Let's go back to the contents of last week. What is? Okay. This is a bus system. It's a power transform or transformation system. Can you see all the purple lines? They are all buses. What are buses? Buses are just some places which can join all the parties together. Generator, loads, stuff. Okay. For example, let's pick up one. Maybe this one on top. You can see here. The top purple bar vertically, horizontally, the G12 is the number 12 generator. This is not a single voltage source. That should be a three-phases balanced voltage source. Okay? So this one single circle is denoting the combination of three separate voltage sources together. Okay? And that is giving the power to that bus 12. And then in the bus 12, at the bottom, you can see there's a line connected to the bus 36. So that is indicating the transmission of the electricity between different buses over the whole system. Okay? So actually, in our, hopefully, good memory maybe, Semester 1, you will be given something like that. And you are going to conduct some analysis by using amp power. Should be amp power. So that is just one separate component in MATLAB. By then, you are going to analyze a system similar to this one. Okay? So you need to understand what does bus mean and what are all these circles or this stuff. Okay? But anyway, just give you some idea how to understand the one-way, one-line diagram. Now we come back to our lecture slides. Single line or one-line diagram. So this part is done. Example 2. I think this is a final example for the chapter 1, I think. Yeah. So in this system, the following figure shows a one-line diagram of a small 480 volts industry distribution system. The power system supplies a constant line voltage of 480 volts. Line voltage is 480. Okay. And the impedance of the distribution lines, so regarding the transmission lines, the impedance is negligible. Load 1 is a delta connected load with phase impedance 10 with 30 degrees ohms. Load 2 is a Y connected load. The phase impedance is 5 with negative 36.87 degrees ohms. So please find the overall power factor of the distribution system. So the lines in the system are assumed impedance less. So this condition given the question. So there will be no voltage drop across the transmission lines when the electricity is transmitted from generator to the load. If there's no impedance, impedance is 0. So no matter how strong the current in the transmission lines, by use Ohm's law, zero impedance multiple whatever current is also equal to 0. That gives us 0 voltage drop across the transmission lines. This is the ideal situation, which indicates no matter how much power provided by the generator, the receiver, the user can receive the same amount of the electricity because the transmission cable is not consuming anything. Okay. And since the load 1 is the delta connected, its phase voltage will be the same as the line voltage, so 480 volts. And for the load 2, it's Y connected, so the phase voltage magnitude will be the line voltage magnitude 480 divided by the square root of 3, which gives us 277 volts. Right. So everyone so far so good? Yeah. So the phase current in the load 1. So in this question here, we are actually focusing on one single phase in the load 1, no matter its pattern, okay? We have already known the phase voltage is 480, and the impedance for each phase is 10 ohms. So 480 divided by 10 by its Ohm's law gives us 48 amps. This current is the phase current in the delta pattern load 1. And then the next step is to calculate the real power and the reactive power by using the formulas we mentioned before. So I believe you should be able to solve that easily by yourself. So I skipped the calculation of power. So any questions regarding power calculation? So in the example 1, we have done this part. So we are using the same formulas, the same methodologies. So I'm not going to repeat it again. Okay. Okay. This is about the load 1. So is that okay? So Ben, okay? Okay. Yeah. So for the load 2, this time we got using the Ohm's law again, using the phase voltage 277 volts divided by 5 ohms. So we got 50.4 amps as the phase 2, as the phase current of the load 2, and then repeating the formulas to calculate the real power and the reactive power for the load 2. Okay, so same thing. Part A is asking the total real power and total reactive power supplied by the distribution system. So because the transmission cables are not consuming any power, so the power consumed by the system are just at load 1 and load 2. In the first part, we have already evaluated the real power and reactive power for the load 1 and the load 2. So the total generated power by the generator should be summation of the total consumed power. So here we are calculating the total real power, total reactive power provided by the generator. Then the power factor for the whole system is equal to cosine theta, where the theta equal to arc tangent, the total reactive power divided by total real power. This is actually the same story in the power triangle at the generator side. Okay, so I don't want to repeat again. Theta is given here. Is that okay, everyone? So I think this calculation is pretty easy. We are using this formula to tell you some story regarding the one-line diagram. So not really the calculation of a three-phase power system. So this part remains same as before. Okay. And the part 2 of the question is asking us to calculate what? Find the total line current supplied to the distribution system. Okay, let's go back to this one-line diagram. So actually, on the left-hand side, you can see the IL is going into the bus A. This is the total supplied current to your loads from the generator. In other words, this current is transmitted in the transmission cables. They are the line currents. Okay? So for this line current, we want to determine how much the IL is. And this IL is divided into 2 parts. One for the load 1, one for the load 2. If you don't believe me, go back to this diagram. Okay, it's a little bit massive, but you can see, don't talk about the voltage, just talk about the current. So let's use one phase as an example. if the current is going up here, at this one single node in this circuit, there are only 3 connections. So the blue line, blue arrow line on the left is the incoming current to this node. There are 2 outgoing branches. One is going down into the node 1. The other one is going to the node 2. So 1 in, 2 out. For the other 2 phases, same story. So 1 in supplied by the voltage source, 2 out. 1 for node 1, 1 for node 2. So in other words, the total supplied current, IL, is equal to the summation of the total withdrawing current, 1 for node 1, 1 for node 2. So if you draw this in the one line diagram, one single input current is equal to the summation of the currents flowing into the 2 nodes. Okay, this whole thing. Okay, anyway, let's see our story. Oops. But for this question here, we are calculating the total line current by using the power. And the formula remains the same, so we just move the square root of 3 VL cosine theta to the bottom of the real power to finish the calculation. But the idea, the final answer should be the same as the way we introduced before. And I think the question is pretty simple. Any questions or issues? This is the end slide for the chapter 1. And actually, after this step, we finish the introduction of the fundamental concepts regarding the 3-phase power system. From the chapter 2 onward, we are going to see other cases. For example, in chapter 2, we are going to check out the models for the transmission cables. And in the later part, we are going to conduct some fault analysis. For example, if the cable got broken somewhere, so what will happen in the 3-phase power system? So different aspects to the 3-phase power system. And the time for now is 4:35. How about let's just quickly go through some general introduction of chapter 2, and then we take another short break. After we come back to the very last part of this lecture, we are going to introduce one single model, the short transmission cable model, and then we finish class. I don't want to make anyone exhausted in my class, okay? I know this session is pretty long. Yeah, it's fun, it's fair. I'm tired as well. I'm standing here for 3 hours. Yeah, so what I want to do now is I'm going to close this chapter 1 lecture slides and move to the lecture 2 lecture slides. And everyone, so please open the chapter 2 lecture slides, and we are going to give you a very, very general introduction regarding the transmission lines. Nothing too much, very general. Okay, in the chapter 2, the topic is the transmission line modeling. So by reading this title, you know, we are going to construct some mathematical models in this chapter for different cases of the transmission cables. Okay, and the reason for this is no cable is ideal. They must have the impedance, and all such cable impedance will consume voltage and power. So we don't like this happen, but they must happen. And we need to use these mathematical models to analyze the behavior of the transmission lines so that we can control how to increase the efficiency and lower the cost. So this is the idea of this chapter. And at the beginning, so the first several pages of this chapter are just talking about some general knowledge regarding the transmission lines. Before we start this part, I can tell you the general introduction will not be tested in the test and the exam. So sit back and relax. Just listen to the stories. Okay, our chapter here will be divided into 5 chapters, 5 sections. Section 2.1 is just a general introduction, just telling the stories. From the section 2.2 up to the section 2.5, we have some serious mathematical models. If you want me to give you some idea of these models, okay, we are going to focus on 3 models. The first model is a short transmission cable model, and the second one is a medium size, and the very last one is the long transmission lines. And you can find the section 2.3 is a special one. It's not one of the 3 models. That is the two-port networks and the ABCD model. That is the abstract mathematical model for all these three transmission line cases. Okay. Okay, this is about the contents for the chapter 2. Okay. Picture starts and story starts. Okay. First of all, you can see in the picture we got some towers and the transmission cables. So they are really very general in the transmissions of the power. And cables are used to carry the electricity from the generator to user. But in most of cases, the distance between the generators to the users may be up to 1,000 kilometers. So the cables will be pretty long. And also, if you are selecting a wrong type of cable, so during the transmission, the decay of the voltage or the loss of the energy will be huge. Okay, depends on the transmission distance. And the other thing is the tower. You know, because of the long distance, all the cables are soft. So they can't just really stand a very long time, right? So we have to use a tower to hang them up, to hold them, to support them. So you can see the towers are just supporting all the wires. Okay, so this is just the general story, and then let's have a look. Okay, do you understand this one? Okay, maybe not. Maybe you can see it around UWA on the street. I don't think you really understand what happened here. Maybe you can say, okay, I can see this pole near the street, and the one line going to that resident's house. What happened there? Actually, one phase is going into that house. But this pole contains all the important components used in the power transmission system. We slow down a little bit and have a look at the picture. This picture is used to do two things. One thing is to transfer the electricity from one side to the other side. The other thing is to finish voltage transmission from high to low. So on the left-hand side, so maybe I can use the marker. We can see 4 lines. 1, 2, 3. So I use the green one for the 4. These 4 lines are going to provide electricity from somewhere else to this electrical pole here. And the 3 yellow lines are hot. They are carrying the positive voltage, so high voltage. The green one at bottom is labeled with system neutral. This is neutral connection. We mentioned in most of cases, the neutral connection can be equivalent if the systems are balanced. But for the resident cells, we can't guarantee all the loads are balanced. So the neutral line is necessary in many cases. Okay? So this is the story here on the left-hand side. On the left-hand side, they are the primary side. The voltages are very high, maybe 800 volts, maybe 1,000 volts, we don't know. But this 1,000 volt is too high for your home use because we are using 220 volts only. So we have to use the transformers to convert this high voltage to low voltage. So in this picture on the pole, this part, and this part, the 3 calendar things are the transmitters, which can be used to convert high voltage to low, or vice versa. Okay? Transformers. Is that okay, Aaron? Yeah, transformers here. But after you finish the transformation from high voltage to low voltage, this low voltage electricity should be output, right? They will be given here, and here. So the low output voltage will be getting out from the transformers and go out to the next place. Okay. And of course, in addition to this stuff, we have some other things like the fuses. They are used to stop some suddenly high current. So if the current is too high, so inside the fuse, some part will be burned out, and this cable becomes disconnected. So we disconnect the connection and to avoid the dangerous situation. Yes, to that. So this is just a small story anyway. Okay. If you say the picture 1, picture 2 are showing you the individual electrical components or a small part of the whole system. So this big picture in this slide is showing us the full view of the 3-phase power transmission system. And this system can be divided into mainly 3 parts. First part is the power generation or production. So this may be far away from our city. so used to produce electricity. And then such produced electricity will be transmitted to us through long distance. So the transmission is in between. By the end, so this electricity arrives at per city and then distributed to different users. So it's the distribution network. So regarding these three areas, so I want to draw attention to the voltage level. In most of the cases, the voltage level at the generator side and user side are pretty much low. Not too low, but should be lower than the voltage used in the transmission. So typically, for the voltage used in the transmission, the voltage are very, very high. The reason we use such high voltage for transmission is for the efficiency of the power transmission. If we keep using, for example, 220 volts for the transmission, so during the transmission, we will lose a lot of energy because all this energy will be used by the electrical cables. We don't want this to happen. So what we are going to do is to increase the voltage during the transmission. If you want to use high voltage for transmission, but at the generator part, you are producing low voltage electricity, you have to use some transformers to increase the voltage from the generator to high level for transmission. And then after long distance transmission, after we arrive at the city, we need to step down the voltage so that the user can use a low voltage at home. So you can see here, we have a number of substations. All such substations are used to finish the transformation of the voltage levels, high to low or low to high. Guys, is that okay? Yeah. And so this is pretty much everything. But you can see, so actually we have already labeled the levels of the voltage at different stage. So normally at the generator, the voltage level is medium, not too high, not too low, just medium one. But we must increase that to very, very high voltage for the preparation of the long distance transmission. And then after reaching next step, so maybe some industry need a medium level voltage of the electricity. So we gave it high voltage electricity. But for other part of the electricity, keep transmitting again and again until reach the end user. For the end user, so we need to just lower the voltage to the standard voltage for home use. So normally 220 or 240 volts at home. This is true for like China, Australia, UK. But I remember in America they are using 110 volts, right? And also in Japan they are using 110 volts. That voltage is pretty low, okay? And yeah, this is the whole story for the systems. Guys, may I just ask you a question here? Do you take trains in Perth? Trains, yes. What's the voltage of the used by train? Can we use 220 volts? Why? Okay, we need to carry the whole train and with maybe hundreds of passengers inside. So we need to give them a lot of power, otherwise they can't drive the whole thing, right? If the voltage is so low, P equal to VI, power equal to VI. If V is low, I, the current, must be huge. If the current is huge, when this huge current is flowing in the cable, large current will produce more heat. So the high temperature will burn these cables. So 220 is too low, okay? Because we don't want very high current. So actually, I don't know details of that, but normally cannot be the 220 or 600 volts. It should be 1,000 volts, okay? 1,000 volts, so that the range of current can be limited to a small safety range for use, okay? But anyway, this is just some story. More things. So what parameters are important for the transmission lines? Generators and loads are connected together through transmission lines, which transport electricity power from one place to the other. And we have 4 different transmission ranges. So for low voltage, up to 600 volts. So that is used to provide power for business and homes. For medium range, so 2.4 to 69 kilovolts. That's tied load centers to a substation with radiation. I think in Perth City. Guys, do you know Carousel Shopping Center? carousel. Behind the shopping center, you can see a big land. That is now a car park. And inside big land, there's no building except one small machine inside at the center of the land. That is the electricity substation. That is used to provide electricity to the suburb around it. Because there's a big shopping mall, so they require a lot of power. So that substation is close by. This whole thing. If you don't believe me, you just go there to check. Okay. High voltage is up to 230 kilovolts. And finally, for ultra high, so can up to 800 kilovolts. This is just some general information. Okay. And a transmission circuit consists of, I think you need to know the following things. Okay, conductors, insulators, and usually shielded wires. Transmission lines are hung overhead from a tower, usually made of steel, wood, or concrete, with its own right-of-way. So for the tower, there may be single circuit or double circuit. This single circuit or double circuit tower means on a single tower, can it support only one set of circuit for one three-phase power system, or it can provide the support to two sets of them, or multiple of them. Okay, so typically for the huge size of towers, it can hold up to 5 or 10 cables for the three-phase power systems. Okay, but small thing, don't worry about. Next one, less than 1% of nationals' total transmission lines are placed underground. Why can't we put all the cables underground? Why? Why expensive? Yes, they need to dig a lot and put the cables underground. Another reason is about the safety. So normally, if you just want to bury some cables underground, the distance will not be very far away from the surface of ground. So when the high voltage electricity going through the cable, so this kind of electricity current will create some field, so magnetic field or electric field. If the people walking around this line here, if the voltage is really very high underground in the cable, so this field may cause some damage, not only to people, but also to some machines. So we don't want this to happen, okay? And also the maintenance cost for such cables will be high as well. So for the consideration of the cost and safety, so we don't really want to just bury this in underground. In most of cases, we hang them overhead. And the distance of these cables should be really far away from the people for safety reasons, maybe up to 50 or 20 meters generally. But if you got really high voltage transmission, the distance will be much higher than this distance. Okay, so yeah, easy issue. Okay, next one. In this page, on the left-hand side, you can see the picture where we bury the cables underground. Just example. Don't worry about that. On the right-hand side, you can see the structure of the electricity transmission cable. I don't want to just read through the whole picture. There are some important things we need to know. Okay, first of all, in the center of the cable, can you see one thing labeled with conductor? This is the most important component used in the transmission lines, which is used to transmit the electricity from one side to the other side. And materials used for this conductor must be metal. This is because tune-outs is done, and normally for each lecture is maybe just tune-outs done. So shortly after this session, when you review this lecture, you can find my recorded lecture is cut off. So I have to restart it. So everyone, take a short break and give me 5 minutes, please. Okay, online students, so to say, we have a short break here. The reason of this break is because the whole AD system is restarting. So please just give me 5 minutes and restarting the system. Once we are ready, we keep going with the lecture comments. I think after the break, we just need another maybe 20 or at most 30 minutes we finish this class. Thank you very much. What time we are going to? How about we finish at 5:20 or 5:30? Okay, online students, we are going to start the very last part of this lecture, okay? Okay, everyone, so first of all, thank you very much for staying late with me in this lecture. And I hope to finish this lecture within 20 minutes or at most 30 minutes. The reason I have to push this lecture because last week, because of the iPad problem, we really lagged behind. So we have to move everybody quickly in this lecture so that we can catch up the progress. Our assignment will be, of course, after week 6, so no rush on that, but we have a lot of content on that. So guys, thank you very much and be patient. I'm going to finish very soon, okay? Okay, the cable thing is done. With that, in the center of the cable, it must be the metal thing because it will be used to carry the electricity power from one side to the other side. And the selection of the materials for this conductor is important. If you are using some wrong materials, so during the transmission, we will lose a lot of energy. So I mentioned that. The best option for the materials used for the connection are just copper or aluminum. So these two things are very cheap and very easy to use and very good conductivity for the electricities. Okay, generally this will be used here. And in addition to the conductor, we have the insulation and the insulation screens. These two things are used to wrap up the conductor for safety reason and also for separating the conductor with the surrounding layers of the cable. Okay, and so I think the other parts are not so important, so I'd like to skip them. Of course, outside of this cable, you can find other layers for providing more mechanical features to hold this whole cable strong enough, something like that. And also we have the outer layer to separate the inside of the cable with the environment. So even though in the windy day, so the environment will not affect the inside of cable, so all this stuff, but they are not important for this unit. This just gives you some general understanding regarding the cable used in the real world. Okay, and tower. And this is another separate story, which is not so important for your study in this unit, but just know it, okay? The tower can be divided into 3 parts. So at the very bottom, you can see we have the tower base. So in most of cases, hold on, something wrong with my type. By luck, I can't draw anything anyway. So the base of tower is used to give very strong foundation to the whole tower. In most of cases, the base of tower is just buried underground and fixed by using some concrete to make a very strong attachment to the earth. Okay, and in the middle part, you can see the tower body. Okay, we do not use the tower body to hang the cables. The tower body is just used to lift the top part of tower away from the surface of the earth, like that. And most of the important components for the power transmission will be hung at the top of the tower. So in this part, I want you to pay some attention. First of all, the structure body of the tower, which include, you can see on top, you can see a beam, right? And also you can see the cross arm and the tower window. So they are all the structure of the the beam, this infrastructure stuff. Our cables are hung at different positions. In most of cases, the ground line will be hung at the top. Very, very sharp tip. Can you see that? There are two small tips on top. So you can see overhead ground line. The ground line are hung over there. And at the middle part of the tower top, really terrible. Yes, I will temporarily minimize the window and try to maximize again. Sorry for that. Okay. It depends. Yeah, maybe, but I just got a new battery anyway. Oops. Let's start again. Just give me 1 second. Maybe use more. So anyway, leave it alone. Leave it alone. Okay. So actually, can you see actually in the tower? I can't. When I just touch it, I just. I click that.
Actually on the draw tab up the top. And then click draw. See the finger with the marker up next to shapes and the pen.
In the middle.
Next to the pen.
Oh, this one.
Yeah, that one.
You're so smart. Thank you so much. I'm just not on this. Thank you so much. Okay, I share it again with the online students. So be patient, please. Share screen and with this thing again. So I hope this works. Okay, thank you guys for helping me. Okay, so here, so in this thing on the top of the tower, are you able to see this thing? Ah, yes, this works. Yeah, this thing called insulators. And the insulator is used to, first of all, hang these cables, but separate the cables from the metal body of the tower. Okay, so actually you can see at the end of these small 4 poles here, there are some dots. These dots are indicating the cables for the power transmission, but these cables are not touching the metal body of the tower directly. The reason is if you really just use the metal body of the tower to hang the cables, in one day, if the shell or maybe the layers of the cable got broken, electricity will go into the tower directly and go to the ground. So the whole electricity will cover the whole tower. It's really dangerous. So we need to use the insulation to separate these cables with the metal body of the tower. Okay, got that? Okay. Oops. Okay. Okay, I see. Thank you. It's fine. I can work this in. Yeah, it works. And next one. So focusing on the conductors. So conductors are constructed primarily of twisted metal strands. Beautiful, right? So, but newer conductors may use other materials, so not important. And in the following part, I don't really want to read through this part. It's just talk about what materials should be used to reduce the power loss during the transmission for the cables. So pretty straightforward thing, okay? So please go through them by yourself if you have interest. Substations. The high voltages used for electrical transmission are converted for consumers used to low voltage at substations. You can treat the substation to be a bigger machine for finishing the transmission from high voltage to low or from low to high. But in this case, please be noted, this is not a single phase transformer. This is a 3 phases one. You have to handle the different voltages from 3 different phases. Okay, and the substations vary in size and configuration, but may cover several acres. They are normally fenced for protecting the people from entering this infrastructure, and are reached by an associated access road. Got that? Okay. Is that okay? I don't want to go into details of this one. It's pretty general. Okay, and okay, the side view of the transformation system. So right of way, we call them as ROW. The right of way for transmission corridors includes land set aside for the transmission line and associated facilities needed to facilitate maintenance and to avoid risk of fires and other accidents. It provides a safety margin between the high voltage lines and the surroundings. And some vegetation clearing may be needed for safety or access. So actually you can see the picture given here. You can see the right of way. So besides the towers and the transmission cables, the land is just free of veggies, free of the trees, and it's just not for human to get access to it. It's just for safety reasons. And for this part, again, knowing that it should be sufficient. Okay, I don't want to spend too much time on the general instruction. Okay, let's skip this part. And access road, do I have to see that? So if you have the transmission tower or some other infrastructures for the power transmission, please prepare a road for the maintainers, for the mechanical or electrical engineers to get access to it to maintain this equipment. Just that, this stuff. Okay, transmission line parameters. The purpose of the transmission network is to transfer electrical energy from the generating units at various locations to the distribution system, which ultimately supplies the load. And transmission lines also interconnect neighboring utilities, which permit not only economic dispatch of power within regions during normal conditions, but also transfer of power between regions during emergency. What does it mean? Okay, actually you can see we are currently in the Netherlands and the Korea suburb. And we have the Shenton Park, we have the Subiaco. In one day, because of the storm, we got the breakout in the Netherlands suburb here. But if the Shenton Park or maybe the Subiaco have their power system working well, so actually they can share some electricity to our suburb. So this is kind of sharing the electricity in some emergencies. Okay, this may happen. So actually you can treat this one to be like the distribution systems. Okay. Finally, all transmission lines in a power system exhibit the electricity properties of resistance, inductance, capacitance, and conductance. Everyone, please notice all these four terms are very important for our study. So we are going to investigate these four terms very soon. The resistance is mostly because of the metal materials used in the cables. For all the metal materials used in the cables, when the current is flowing through them, so these particles in the materials will try to resist the current. And from our view, they can be treated to be the resistance of the materials. For different materials, the resistance will be different. Okay, inductance, important. If I'm just using a metal cable to transmit the power, where we got inductance? That answer is actually given here. Did you notice we mentioned the conductor of the cable is made of twisted metal threads. If you twist a metal thing, you are making an inductor. In your foundation unit, like the energy long time ago, you are using inductor, but actually inductor is same as resistor. The only difference thing is, in the resistor, we're just using a piece of high resistance materials, but for inductor, we twisted it. So in addition to the resistance, we have inductance on it. But we are making our power transmission cables by using the twisted metal threads. So this thing will produce inductance when the power goes through it. But here, I want to draw attention. If you got AC current going through such kind of cables, yes, we are producing inductance. But if you are using DC, the direct current going through such cables, no inductance will be produced because only the time varying current will produce inductance. But DC is not time varying current. It will not produce inductance. Okay. But anyway, this is just a side note. Capacitance. In most of the times, the capacitance is built up between the cable and the ground. So we have the high voltage electricity in the cable transmitting. Cable is separated from the ground, insulated. So such kind of thing make a huge capacitance. Okay, that is capacitor. And the conductance is how good we conduct the electricity. It's a small thing. Okay. Models. The inductance and the capacitance are due to the effect of the magnetic and electrical fields around the conductor. These parameters are essential for the development of the transmission line models. And the shunt conductance. So everyone, could you please highlight this shunt conductance? So when we studied the 3 different transmission line models in this chapter, first one, short model. Second one, medium model. Very last one, long model. Out of these 3 models, the hardest one is the very last one. Very complicated model for the long transmission cable. The key difference in the long transmission model compared with the other 2 models is the shunt capacitance. Okay, shunt conductance. This accounts for leakage currents flowing across insulators and pathway in the air. The leakage currents are negligible compared to the current flowing in the transmission lines and may sometimes be neglected. This is true, but if you want to develop one very accurate model for the transmission cable, we can't neglect all these details. By then, in the long transmission cable models, we are going to face this issue. Okay, this is just the general introduction. Now let's talk about the most important part for the chapter 2. 10 minutes, okay? And the transmission lines are characterized by a series of resistance. Okay, resistance is because the materials we used in the cable, okay? And inductance is because we twisted the metal set, okay, per unit length, and by a shunt capacitance per unit length. These values control the power carrying capacity of each transmission line and the voltage drop in the transmission line at full load. Don't worry about the full load. We are going to have a look at what does full load mean. The other term is a non-load. So we talk about these 2 things shortly, okay? The transmission line models are classified based on their transmission size or transmission length. If the transmission length is pretty short, less than 80 kilometers, so we treat that to be short transmission line model. If the transmission distance is between 80 and 240 kilometers, that's a medium size. Finally, if the transmission size is greater than 240 kilometers, so we are going to use a long transmission model for such transmissions, okay? And now, we started from the first, the easiest transmission model, the short transmission line model. Typically, the distance should be smaller than 80 kilometers. The short transmission lines are modeled as a simple series resistance and inductance. Why don't we consider the shunt capacitance? The main reason is the transmission distance is too short, less than 80 kilometers. In such short transmission distance, the shunt capacitance is so tiny, so we ignore that here. Okay, so in other words, for the short transmission lines, we focus on the resistance and the inductance of the transmission line only. And in the diagram, you can see on the left we have the VS, on the right we have the VR. This S stands for the sending end. The R is for the receiving end. Okay, so the power is given by the sending end and received and used by the receiving end. Between these 2 sides, we are using 1 transmission cable to make connection in between. So of course you can see there are 2 lines. At the bottom it's just a flat line, and on top is just a line with the R and the JXL. Actually, the bottom line is essential but not important. In most of cases, the bottom line is used to connect the 2 negative parts of the receiving and sending sides. They are connected to ground in most of cases, so not important. But for our analysis of circuits, they are essential. Okay. So we talk about the transmission lines. In this diagram, the transmission line is the line given here. We focus on this one. And because we said for such transmission line, we can't ignore the resistance and inductance. So you can see in the line, you got 1 resistor. You got resistor R. You have the reactance for that inductance XL. Okay, so these 2 things cannot be ignored. So what is R? R is the total resistance of the transmission cable over the whole range of the transmission. But in this question here, we have already known what is the resistance per unit size. Read that? I can't find it. So anyway, so this lower R in the equation is used to denote the resistance per unit transmission distance. For example, 10 ohm per kilometer. That's too small actually. Or 20 kilo ohm per kilometer. This is the resistance per unit transmission size. Multiple the total transmission distance. So this capital R is giving us the total resistance of the whole level used in this case. For the reactance, the same thing. The lower X is used to denote the reactance per unit size. Multiple the total transmission distance, the capital X becomes the total reactance of the whole cable. Okay, got that. And after we know this thing, based on the circuit, at the sending end, we are giving a Vs. At the receiving side, we got a VR. If the Vs and the VR are the same, okay, that's perfect. No matter how much I give from the sending side, so I can receive the same thing at the receiving side. That's too ideal to be true. So actually, your cable will consume something. But how much voltage potential will the cable consume? So we're just using the line current multiple the impedance of the cable to calculate the total voltage drop during the transmission. And then the total supplied voltage, Vs. The total supplied voltage, Vs, should be the summation of the voltage drop across the transmission plus the voltage received by receiver. Total supply is equal to the summation of the total consumption. Got that? Okay? And I think the next step is pretty easy because we are just converting the Z impedance of the cable to the R plus J by XL. And then that's easy thing. So if you want to view this story from the viewpoint of the receiving side voltage, so we can say VR is equal to Vs minus R by I minus J by XL by I. I think everybody have already got TAD and MTAD as well. The time is good for us to finish now, and I think at this point is just sufficient for our start in chapter 2. And in our lecture, in next week, we are going to keep discussing the next part of the section, chapter 2. In our practical class tomorrow, Thursday, I'm going to go back to the chapter 1 because actually this tutorial session tomorrow morning was shifted from Monday this week. Actually, that is the practice session for last week. So I will go through the tutorial questions in the tutorial 1. And I'm going to be here at 9 and finish at 9:45. Because after 9:45, I have another class. So I have to stop and jump to the other class. So we have only 45 minutes, and I will try my best to go through as many questions as possible. If you have any particular question to ask, welcome to bring a question to me. Okay? All right, thank you very much for attending this lecture, and see you tomorrow morning. Bye for now. See ya. That is really? Yeah. Crazy. Should be, because that class has already been scheduled by computer. If it's not recorded, we may find some time to just go through some details together. But I hope it can be recorded. Okay? Let's have a look at what happens after tomorrow tutorial. Okay? Yes. Tutorial 1 questions. All right, yeah. Doesn't matter. You don't have to. So I will go through the questions in the lecture. Try our best. Yeah, just no. Different venue. Is GGGL which 107? Another building, not here. So check the timetable. You can see the
Another class at the same time. I don't know.
I have as well, but I have the other staff to help me.
The other ones are
Is class okay today? Is class today okay? Yeah. Okay. See you. Take care. Okay, Alice, thank you for attending the class. And now we are finishing this lecture. The remaining part of the chapter will be discussed in our lecture next week. Tomorrow morning, between 9 and 10, like 9 and 9:45, we are going to use 45 minutes to go through the preparation of the tutor 1. So I hope I can see you again tomorrow. Okay, everyone, bye for now. Thank you very much. Goodbye, everyone.哦，谢谢。我就想低一点，我不想那么高，高了以后我得架着行，低了以后，哎，无所谓了，反正是站着就够累的。我还没看呢，不过很简单，应该是。就是，哎，review 有啥可难的 ？Easy stuff, don't worry about that. Okay, see you. Thank you. 何止3小时，今天站了得有6个小时。我还别的课呢，又不是这一个课，不是别的课，是帮文雷的课。哎，你认识文雷吧？我们俩今年大半上一个本科生课。然后，哎呀，这个就跟那什么样，这是体力活，说实话，非技术工作。